Everyone, in this video we are going to be looking at the Bernollis equation as one of the methods for solving differential equations. Okay, now the equation, Bernollis equation, is of the form y raised to the power minus n dy dx plus p y raised to the power minus n plus 1 plus equal to q. Now remember that your p and q are functions of x. Okay, then the solution to the Bernollis equation is that we will reduce the equation to this, okay, which is a first order linear equation. Okay, so and how do we do that? We start by saying let v be equal to y raised to the power minus n plus 1, and when you differentiate, remember the power comes down, so you get minus n plus 1 y raised to the power minus n. Okay, that's, you get that by saying y raised to the power minus n plus 1 then minus 1, which gives us y raised to the power minus n. That is why we have that. And so if we now divide through by dx, we are going to get this. So we now have dv dx now becomes 1 minus n y raised to the power minus n dx. Okay, so then your y raised to the power minus n dy dx now becomes, making it a subject of formula, it becomes 1 all over 1 minus n dv dx. In order not to confuse us, I would like to go that all over again. We say that we are saying let v be equal to y raised to the power minus n plus 1. Okay, so if we differentiate v, dv now would be, the power here comes down, which is minus n plus 1. Then we have y raised to power. If you subtract 1 from the power, you are going to get just minus n. Okay, and dv, because that's an implicit, sorry, dy, that's an implicit differentiation. Okay, so we can choose to divide through by dx, and if we do that, we are going to get over dx, and this is also over dx. Okay, now your y raised to the power minus n dx, which is this now, means I will divide both sides by this minus n plus 1. Minus n plus 1 also means 1 minus n, so this cancel this. That's the same thing here. I divide 1 minus n. Okay, so that's the reason why the y raised to the power minus n dy dx now becomes 1 over 1 minus n then dv dx. Okay, so that is what we replace it as. Now let us quickly look at a question here. We have dy dx plus y equal to y squared into cos x minus sine x. This is not looking like a Bernollis equation. Remember, the Bernollis equation must be such that dy over dx, okay, plus, sorry, y raised to the power minus n dy dx plus y raised to the power minus n plus 1p is equal to q. Okay, so your q here should be, so we have to do something about this, meaning that we can choose to divide through by y squared, and when we do that, we are going to get y raised to the power minus 2 here, and here y divided by y squared gives us y raised to the power minus 1. Then you eliminate y squared here. Now this is already looking like a Bernollis equation. We can start by saying let v be equal to y raised to the power minus 1. Okay, so it means that dv would be, if the minus 1 comes down, we'll get minus 1y raised to the power minus 2 dy. Okay, so if we differentiate both sides by dx, we get over dx, and so it means that y raised to the power minus 2 dy dx is equal to dv dx. So that's the reason why this now leads us to this. Okay, dv dx. So where we see y raised to the power minus 2 dv dx, we replace it, dy dx, we replace it with dv dx, then plus, actually it should be a minus there, then your y raised to the power minus 1 is already v according to this here. Then here you have cos x minus cos x plus sin x. you may wonder why we have here this. Remember, from here you can notice that y raised to power minus 2 dy over dx is equal to minus dv over dx. Okay, so if we put it that way, then it means we are supposed to have something like this. We are supposed to have minus dv dx, okay, then plus v, okay, equal to cos x minus sin x, cos x minus sin x. Now, but because we multiply through by the negative number, you now get dv over dx, and this is minus v equal to minus cos x plus sin x, multiplying through by the negative number. That is how we arrive to this. Okay, so, and this is already looking like our first order linear equation. And remember, what a first order linear equation must look like this, which is dy dx plus py equal to q, and that is exactly what we have here. So, and the first order linear equation, we start by finding the integrating factor. Here your p, from what we have here, your p is 1, okay, or you can say minus 1. Then your q is minus cos x plus sin x. Okay, so our integrating factor here is exponential integral of minus dx. We are supposed to say exponential integral of minus 1 dx, you know, but it's the same thing. And when we do that, we are going to get exponential minus x, because integral of dx is x. Okay, now that leads us to the solution to a first order linear equation, where rho v is equal to integral of rho q dx plus c. Okay, your rho, which is the integrating factor, is exponential x here. Then you have your v equal to integral, your rho is this, then your q is sin x minus cos x dx plus c. Now this is looking a little more difficult to integrate, but it is not impossible. We can start by opening the bracket. So that's how we get this, and we got this. When we open a bracket, exponential minus x times sin x gives us exponential minus x sin x, and we now have minus exponential minus x cos x. Okay, now to integrate this, since this and this looks alike, and derivative of cos x will give us sin x, and the only way we can solve problems like this is by integration by parts. Okay, so we can leave this and integrate this by parts. So that's why we have that's the formula for integrating by parts, uv minus integral of v du, and we are letting our u here to be exponential minus x. Okay, then we are making our dv to be cos x. Okay, and if your u is exponential x, it means that your du, derivative of u, would be minus exponential minus x, differentiating that. Then your v, we get v by integrating dv. Integrate cos x, we are going to get sin x. Okay, so we are going to use this and substitute it into this equation, and when we do that, we are going to get this exactly. We have this on the left hand side, exponential minus xv. Then we have this already, then minus, this is uv. Okay, this is our u, this is our v, based on what I taught us. Then minus integral of v du. It's supposed to be minus here, but because of what our du is, it gave us plus. So this is v du, this is du, and this is v. Okay, according to our formula. Now when we open the bracket, you will notice that at the end of the day, that integral of minus sin x dx, we cancel this. That's, if we open the bracket, we are going to get some of the right hand side, please. We're going to get integral of exponential minus x sin x dx, then minus exponential minus x sin x. Okay, then minus exponential minus x. Okay, integral of exponential minus x sin x dx. Now by subtraction, you see that this can cancel this, and we are left with just minus exponential minus x sin x. That is how we got this. Okay, so, and which is the solution to the first order linear equation. But remember, we started by saying let v be equal to y raised to power minus 1, and that is exactly what we have here. Okay, so let's quickly look at another example here. We have this to be y squared dy dx equal to, okay, plus 1 over x y cubed equal to x squared plus 4. Now, from what I see here, there is nothing to rearrange here. Since your y cube here, when you differentiate y cube, you are going to get y squared. So we can start by saying let v be equal to y cube, and if your v is y cube, it means that dv will be equal to 3y squared dy. Okay, implicit differentiation. So if I divide both sides by dx, I'm going to get dv dx equal to 3y squared dy dx. Okay, so if my y squared dy dx, which is what we have here, making a subject of formula, we are going to get that y squared dy dx is equal to 1 over 3 dv equal to 1 over 3 dv dx. Okay, so that's the reason why we have this. And if we say this, if we substitute this now to the original equation, we are going to get this. We are going to get your y squared dy dx now is now 1 over 3 dv dx. Okay, then y this now is plus 1 over x times v. Your y cube is v, remember, then equal to x squared plus 4, x squared plus 4. Now we can, this is not looking exactly like a first order linear equation, so we can choose to multiply through by 3. And if we do that, we are going to get dv dx, okay, equal, okay, plus, sorry, 3 over x v, then equal to 3 into x squared plus 4, which is exactly what we have here. That is how we achieve that, which is a first order linear equation, which looks like dv dx, okay, plus pv equal to q, which is what we want. Okay, so, and how do we go about that? We get our integrating factor, which is exponential p. Remember, our integrating factor is supposed to be exponential integral of p dx. So our p here is 3 over x. So we have exponential integral of 3 over x dx. An integral of 3 over x dx is the same thing as 3 ln x. We've done that a lot of times, and which is the same thing as s cubed. You know, remember, your exponential 3 ln x is the same thing as saying exponential ln x raised to power 3. And ln usually cancels exponential, which gives us back our s cube. Okay, so now the solution to a first order linear equation, which is rho v equal to integral of rho q dx plus c. Okay, now that now leads us to the next. So substituting values now, that's our rho v. So our rho is s cube v equal to integral of this is our rho, which is s cube, then this is our q, then dx. Okay, so we have s cube v equal to integral. If we open these brackets, we're going to get this. Okay, so and the next is to integrate this. Integrating x 3x5 is we'll get 3x6 all over 6 using applying our law of integration, and of course 3 can go here too. So that's how we got 1 over 2x6. The same way, integrating 12x cubed is going to give us 12x4 all over 4. Okay, and 4 can cancel here to go 3 times. So that's how we got 3x4 plus c. Okay, so at this point here, we can now substitute the value for v, which initially we said is y cubed. So our solution now is s cubed y cubed equal to half x raised to power 6 plus 3x4 plus 6. If you want to make y subject of formula, you can choose to divide through by s cubed. Okay, and but we can leave it this way. Thank you very much. I wish you the best.